In this video, we'll talk about graphs of rational functions. This will kind of be an introduction into some features that they have. So let's dive right in with an example. Let's say we want to look at y equals 1 over x. So this would mean that if x is 1, y is 2. If it's 2, y is a half, then a third, then a fourth, so on and so forth. Now, we get kind of an interesting looking graph here if we plot this in a software of some sort. It gets closer and closer to 0 as I go further and further out to the right, and that would make sense because, well, we're increasing this denominator. So it's going to take this 1 and cut it into smaller and smaller pieces. And what we'll find here is that a horizontal asymptote is created. Now keep in mind, an asymptote is a line that a function approaches but doesn't cross. So when we're thinking about what happens as I allow x to proceed to infinity, as it gets bigger and bigger without end, well, my y value is going to get smaller and smaller, but it can never go negative, because when I take a number divided by a positive number, or a positive number, in this case 1, divided by a positive number, in this case x, it's always going to be positive, but each one is going to be smaller than the last as I move to the right. So we may also notice that there's a vertical version of this. So there's a vertical asymptote, and that happens because if I allowed x to be 0, it would result in an undefined value. So if we think about this as x kind of gets closer and closer to 0, well, when x is a half, y is 2. When it's a third, it's 3, so on and so forth. As I kind of proceed, that means that as I'm dividing by a smaller and smaller number here for x, as I get closer and closer to 0, my y value is actually going to increase. Hence, it's going up here. And then very similar train of thought for the negative side of this curve. We're just looking at more negative values, but that's kind of why this function looks the way it does. So in general, when we're looking at a rational function, and a rational function would be where we have f of x is equal to a of x over b of x. And this is, again, kind of a weird, funky notation. It's something that a lot of textbooks use. But their way of explaining this is saying that, okay, these two things are both polynomials. So like an example of a radical equation, or, a rational equation, would be, say we have x plus 1 over x squared minus 49. This would be one example. Both of these expressions in numerator and denominator are polynomials. Now, there are some key features, some characteristics that we can use our structure to find. So when we're talking about key features for these graphs, a lot of what we're really looking for is we're trying to find these asymptotes. We're trying to find these lines that they do not cross. So when we're looking at a rational equation, well, if we're looking for vertical asymptotes, that one's actually not too bad. They will happen whenever my b of x is equal to 0. So I will set it equal to 0, and then I will solve. And we'll do an example here in a bit to kind of show how this is useful and how it's helpful for making the graphs. And if we're looking at horizontal, there's actually a couple different schools of thought. The first school of thought that I like is we look at what's called end behavior. And I like this because it's one thing. I don't have to necessarily remember a bunch of different contingencies for when I have a horizontal asymptote, when I don't, or when it's a particular value, when it's 0, when it's not 0. And the idea is what happens as x approaches the end. So either infinity or negative infinity. Basically, I'm trying to answer the question, okay, what happens to y as this happens? And it would be, I'm going to fill in this blank here. And the idea is, I'm going to look at the leading terms. So that would be the biggest powers of x on both numerator and denominator, and I'm just going to simplify that expression as much as possible. The other way to look at it would be you're looking at degrees for both numerator and denominator. If the degree of a of x is greater than b of x, meaning like say the leading term here is x cubed and the leading term here is x squared, well then there's no horizontal asymptote. This top term is eventually going to take over and it's going to peel off towards infinity or negative infinity. It's going to grow. If we're looking at something where they're equal, then we're looking at the ratio between the leading coefficients. And if we are looking at a case where the degree of b of x is greater than a of x, so if we were to flip these two, then the horizontal asymptote would always be at 0. Now that's a lot of things to remember all at once, and it's a lot, especially with an introductory lesson. That's why I'm a huge fan of the end behavior, and I'll show you why here in an example. So let's say I wanted to graph y equals 1 over x plus 5. I can do this. It's going to be a little bit different. The idea is, okay, if I have my coordinate grid here, okay, cool. I'll do 1 through 5 on both the positive and negative. But now what? How do I graph this thing? It seems a little difficult. So here's what we're going to do. First, we're going to find our vertical asymptotes, which I'll abbreviate with VA. And how I find that is I'm going to set x plus 5 equal to 0. And then I'm going to solve for x. So that tells me that at negative 5, I have a vertical asymptote. That means that I don't cross that line. Now I'm going to think about my horizontal asymptote. And the idea is I'm going to ask myself, okay, what happens to 1 over x plus 5 as x gets really, really big? Right? So the idea is I'm only going to look at the leading terms, and in this case it's pretty simple. We'll look at examples in another video where it's a little more complex, but really all I have to look at in this case is the 1, because it's the only thing up there, and the x, because that's the leading term. Now we know that as x increases, as it goes to infinity, that means that 1 over x goes to 0, which tells me I have a horizontal asymptote at y equals 0. Which means the axis line is my asymptote in this case again. Now, I know that when I draw this, I can't cross these blue lines. So either it's going to look, it's going to have some sort of curve to it. And that's where I have to kind of test on either side of my vertical asymptote to really determine if it's above or below. So I'm going to pick a value less than. Let's say I try negative 6 in here. Well, if I do negative 6 plus 5, that's negative 1 divided by, or 1 divided by negative 1 is negative 1. So that would tell me that it's below this thing, which means it can't cross either of these blue lines, so it's got to look something like this. Now, similarly, I'm going to try another value. For my sanity, I'm just going to pick 0 for x. For the other piece, I'm doing the right side of the break here. So let's plug that in. I'll have 0 plus 5 is 5. 1/5 is positive. It's above the line, meaning that all the values have to be above as well. So if I was to graph, or at least provide a sketch, this is what it would look like. And in order to do that, I need to find the asymptotes. Now, this is one lesson where we're kind of just looking at the intro. We're going to get more complex and we're going to get more practice with these. So this is just kind of a start.